All right. So let's continue on. We have one more topic in logic gates and combinational circuit that I want to cover, which is basically synthesis or solving for a particular equation. So there and right here. So combinational logic is so called because we take various logic gates and we combine them to implement logic circuits, right? So a AND gate implements A and B. So the output of a AND gate C implements A and B, for example, right? A NOT gate is basically the inversion of your incoming signal. An OR gate is simply the sum of your incoming to input signals. Similarly, if you have more than two inputs, whether it's 3, 4, 5, does not really matter. You can create a logic circuit to fulfill that requirement. So in this case, we are given an equation. The equation has 5 inputs, A, B, C, D, and E. Okay. So it has inputs, which are labeled as A, B, C, D, and E. And one output labeled as F. You're asked to implement this logical equation using logic gates. So we combine various forms of gates and try to implement this equation. So the way we typically do this is by drawing out all the input lines on the left side and then take each term individually. So here we have A and B naught and C. And then you have A and B and C. And this is C plus D and D naught plus E. Okay, so you take each term independently and you see which gate would fit. So if you're trying to do, well, first thing is draw out our input lines. So this will be A, B, C, D, and E. Now, we want A and B naught and C, right? So we have a 3-input AND gate, 3-input AND gate, and this should give us A and B and A and B naught and C, 3-input AND gate. Make sense? Now, we can branch out all the inputs as we need. B naught means we need to have a inverter somewhere in there. And so this gives us B naught. This is going to be A, this is going to be C. Right? And then C is going right here. And wherever there is a connection, I'm going to insert a dot like this. Okay, insert a dot. If it crosses over without this dot, it means there is no connection. So this means there is a connection. This means it's crossing over, no connection. You can do the loop thing too. The loop thing is you're jumping over. It's a loop thing. Typically, you won't see this. It's easier to just either have a dot or absence of dot. So if a dot is present, that means there is a connection. If the dot is not present, then it's not connected. Yes. So if you have an electrical wiring diagram, you might see something like that. Loop thing. Again, it's the same. It's jumping over, so no connection. Okay, so where was I? Oh, so we are done with the first one, right? A and B naught and C. Does that make sense? And so we proceed and we implement the logic using gates in exactly the same manner for the rest of the components. So now we have another AND gate, and we require another 3-input AND gate for A, B, and C. And so we have A, B, and C. So C goes directly in there. B goes in there. And A, let's see, how do I want this? So we have the second term. Then the third one is actually it's an AND gate. It's a product of 2 OR gates. So we'll draw the AND gate somewhere out here, because when we first begin, we have no idea where the circuit would fit in. So we'll draw it out here. And the 2 OR gates have C, D, D naught, and E. So and then C plus D and D naught plus E. So E is right here. D naught will require a NOT gate. So this is going to be D naught and E. This will be D naught plus E. And this was C plus D. So C, oh, pen's acting up today. I don't know why. C, C, D, C plus D. And then what do we have? We have a 3-input OR gate to signify this big operation right there. So we take the output of each of these. So this is F. That's how you would create your circuit. That is the implementation of this. And so if you take it step by step, you can implement any equation using this kind of logic circuits. You can build any circuit using this. Now, obviously, if you take a look at the expression and you look at the circuit, it seems a little bit complicated, right? And that's where De Morgan's laws and other laws come into the picture. We can reduce these, we can reduce this equation by using those techniques and those laws. And then perhaps if you're able to reduce it, you might not need so many gates. Okay, so for instance, C plus D and D naught plus E can be reduced. We can change the AND operation to an OR operation, right? We take C plus D naught plus D naught times E naught, and you can change the operation. You can reduce the expression. So that is in the book, there is a section where they talk about that. It's not really, sometimes I go over in 321, other times I skip it. This time I think I'm going to skip it. Yes.
Are you able to factor the magnitude A
D and what?
B and not B.
B and not B.
So you said that B must not be if you want a one. So then since you have, you scroll up to the original equation. In the first two, you're given A and a B in both.
Yes.
Factor those out. And then,
Yes.
and then sum the two.
Yes, you can do that. I think there's also where you can multiply. I think it becomes D and D naught, and you can get rid of that also. And so that's a good point, right? So anyway, that actually reinforces the point that if you take the equation and you reduce it, you're able to actually implement it with fewer gates. Okay.
I've had to build a bunch of cables with schematics and work on like that in the past. And stuff that I've heard Google. What does this mean then? Like having all these gates is just different information you can send them, or like
Yeah, gates is basic. So at its heart, a gate is simply built out of transistors. Simply built out of transistors. Typically MOSFETs. Okay. But the reason it's called gate is because it acts like a gateway. Depending on the input, you have.
oh yeah, okay. That makes sense. 'Cause I would
The
do
reason we start digital by teaching about gates is because these are the fundamental building blocks. These are the fundamental building blocks of all computer circuits. And so that's why we start talking about gates. But in again, if you talk about in real life, there's very few places where you'll actually take something like this and actually build. It's more for like teaching tools. You could build a entire feedback system to control an operation of a system, whether it's a thermostat control or whether it's a like big machine that's churning out some
Yeah.
sort of product.
Yeah,
There's always a logic component that's built into it.
yeah, because that's where
And
I've
so,
seen the
yeah.
stuff kind of similar to that where I was like,
Yep.
now it's kind of making sense a little bit
Yeah.
more.
So as non-engineers, especially if you're like mechanical or industrial manufacturing engineers, you'd encounter something like this a lot.
Yeah, that's what I've
Yeah.
seen.
So as non-engineers, you would not be called upon to like design something like this. But if there's an E on the team and they are designing something, then it's, you should be able to understand what they're talking about. Yeah. So as I was saying, this is known. I don't know what's wrong with the pen. These circuits are known as combinational logics because you're combining different gates together and creating and implementing some logic equations, right? But they don't have any memory. You apply a input, you get an output. If the input goes away, the output goes away. It does not store that memory. I mean, it does not store that output. Okay. And that brings us to a second kind of logic circuit, which is known as sequential logic circuits. The sequential logic circuits, there is a possibility, depending on the design, that it stores the output result even if there is no input. Okay, so input is applied and then it's removed. The output is saved in there. So we call sequential logic circuits as having some sort of memory. Combinational can be called as memoryless. Okay, combinational logic can be referred to as memoryless. Sequential circuits can be said to have memory. And more often than not, sequential circuits involve some sort of feedback, meaning you take the output and you feed it back into the input. And you'll see that in just a couple of slides. So sequential logic circuits, again, we're using logic gates to build them. But the difference between a sequential and a combinational is that it can store the information even though the input's not present. And for also that reason, we also have what we know as a clock input to some of these circuits. Okay, clock input. The clock input synchronizes everything. Clock input synchronizes everything so that everything has to take place in a sequence. Especially if there is feedback from the output going back into the input, then we need a clock to actually synchronize everything so that everything occurs in a sequence, and hence the name sequential logic circuits. And what we term or refer to as a clock signal, or a clock input, is simply a rectangular pulse or a square wave. So a rectangular pulse or a square wave. Typically, it's just a rectangular pulse, where the high level could be +5 volts, low level would be 0 volts. So digital circuits, when they first started out, had a level of +5 volts, and then now we have digital circuits with a level of 3.3 volts. So it could be +5 volts, or it could be 3.3 volts. And it's basically clock is simply on for half the time and it's off for the other half. And so you have logic 1, logic 0, logic 1, logic 0, 1, 0, 1, 0, and so on and so forth. This is one cycle. And if you remember from 201, chapter 5, number of cycles in 1 second of time is basically the frequency of that waveform. F is basically the number of cycles I might have to restart this.
Yeah, it was good. They restarted it before, huh?
No, not Zoom recording. Okay, so as I was saying, F is number of cycles per second. It's also the speed of the CPU that we all talk about for our phones, tablets, computers. And that basically is the clock frequency. That is how fast your clock is running. So a 1 gigahertz clock or 1 gigahertz CPU has a clock that runs at 1 gigahertz speed, meaning 1 into 10 raised to 9. I had to think for a moment. 10 raised to 9 cycles per second. So what is it? 1 billion cycles a second? It's running that fast.
What's typical for a CPU?
I think the Pentium 100, I mean, processors that came out early on were, they used to run like kilohertz. Now, anything less than 1 gigahertz would be considered mediocre. So, I mean, like even the smartphone CPUs run at like 2 gigahertz, and they have like 4, 5, 6 cores running all at once.
I think I might be misremembering this, but I think Windows 11 requires 1 gigahertz.
Well, it doesn't require that. It just, so they are moving. So we're going on a tangent, but it's kind of relevant. So the big thing in modern computing and modern electronics or modern world, if you will, is basically cybersecurity. And Windows 11 is a big change, is because the way they're going to implement is, and I don't fully understand how they're implementing this, but they have a system called Secure Boot and TPM. TPM is for it's security monitoring chip. Okay, so there's a TPM chip inside the motherboard. So there's 2 versions of CPM 1 and 2. So if your PC does not have TPM 2 or Secure Boot, then it does not meet the security requirements. But it is possible. I mean, they say it's 1 gigahertz, but it is possible to run it at a lower frequency. It will work just fine. I installed it just because I'm a tinkerer like that. I installed it on like a 10-year-old PC, 10-year-old laptop, and it works just fine. But you have to bypass all the security requirements. Shouldn't have said that. I'm recording. Anyway, it's not as if it's not illegal or anything. They still allow you to download and install it on there. But again, if you want to know how to do that, I'd be happy to talk to you after class. Let's continue with this. So the basic, well, this is not Hawaii, it's still California. We can talk about flip-flops. But in electrical engineering, flip-flops are basically a class of electronic circuits that is the basic building block of a sequential logic circuit. So here is the most basic of all. You have two NOT gates with the output of each gate fed back into the input of the other. Okay, fed back into the input of the other. So here's the feedback. Here and then here, right? Crisscross. And then for all gates, you would see two outputs. You will have a Q, so output Q, and then Q naught. Q naught. At any given point, Q and Q naught will always be opposite. So if Q is equal to 0, Q naught will be equal to 1. If Q is equal to 1, Q naught would be 0. Now, this is a this diagram is self-contained, but obviously you need to have some sort of input, like a clock signal or something going in. But this suffices because it's the place right at the bottom where we are going to build our explanation for everything else that follows. Okay, so if Q is equal to 0, what happens? If Q is equal to 0, 0 is fed back in here, output is 1. And that output is fed back in here. Output is 0. If Q is equal to 1, fed back into, let's call this A and B. Then B becomes, output of B or Q naught becomes 0. That 0 is fed back in here. And now you have an output of 1. And so it's continuous flip-flopping between two states. Okay, flip-flopping between two states. So as long as an external input is not applied, it'll keep the outputs stored in memory. Keep the output stored in memory. So even if you take away the input, the output does not change. So now, this is just an example of how the output is connected and fed back into the input. It's not a very useful circuit just by itself. A more useful circuit is something like this, which again, in terms of actually real world application right now, even this is pretty much useless. And there is a reason for that. So this is known as the SR flip-flop. The S and R stand for set and reset. So it is a set reset flip-flop built out of NOR gates. Okay, set reset flip-flop built out of NOR gates. And the set indicates that the output Q would be equal to 1. So when set is 1, output Q is equal to 1. When reset is 1, output Q is equal to 0. And hence set and reset. A set means 1, a reset means 0. So think about the inputs to a NOR gate when it's 0. A NOR gate has this truth table. NOR gate TTE. You have two inputs, A, B. NOR gate is basically the NOT of a addition or OR gate, right? So if you have two inputs to a NOR gate, you have 0, 0, 0, 1, 1, 0, and 1, 1. What is the output? Output, I'm going to say C, is going to be 0 plus 0 is 0, so you're going to get a 1. For everything else, what is it going to be? Zeros. So a NOR gate will have a high only when both inputs are low. For any other input, output is going to be 0. Okay, output is going to be 0. So R and S are basically two inputs of the NOR gate. The other input comes from the output of the other gate. So output for the S input, Q naught, goes into, oh, there's the jump. There's the jump. And I just said it's not widely used, but there's the jump. I just realized it. This jump. Anyway, if we are using this dot indicator, then you could just have a cross like this. It would mean the same thing. Anyway, so the output is being fed back into the input, Q and Q naught. So if R and S are zeros, doesn't really matter what the other input is going to be. The output's going to be the previous state. Right? If you look here, if any one of the inputs right here is 0, only possibility right now is Q and Q naught could be 1, or Q and Q naught could be 0 or 1, but the output would be 0. So it remains in a previous state. And I'll go through and analyze every step. How much time do we have? You have a couple of minutes. Okay, so let's assume Q was 0. So what is Q naught? 1, right? That 1 is being fed into that NOR gate up top. Let's call this A. Actually, you know what? Let's just call it R and S. So if the R gate has 0 and 1 as the input, what's the output? 0, right? So it remains as 0. And that 0 is being fed into the S gate. What is the output of the S gate? 1. So it remains at 1. Now, let's say Q was 1 and Q naught was 0. Let's erase this. Let's say Q was 1 and Q naught was 0. What happens? This becomes 0, 0. So if R gate has 0, 0, output remains 1. That 1 is fed back into the S gate. S gate now has a 0 and 1, or a 1 and 0, if you will. Output remains at 0. So when both inputs R and S are 0, the output of the flip-flops remain in that previous state. They do not change. And hence, we say Qn, which is the output, Qn minus 1 is referred to as the previous state. Okay, Qn minus 1 refers to the previous state. Qn plus 1 refers to the next state. Next state. But does that make sense? When both inputs R and S are 0, 0, the outputs Q and Q naught remain in the previous state. Doesn't matter whether they were 0 and 1 or 1 and 0. They will not change. They will not change. Okay, it's 2:01, so well, I'm going to have to stop right here and pick up here on Wednesday. And to explain this, I'll go a little bit slow on Wednesday too, but once we are done with this, then I'll pick up the pace. So I want to make sure students understand how this works, and then we move on to them.
What do we have left?
Just sequential logic circuits. That's all we have
Okay, cool.
for the most part. Yeah, and then computer architecture next week. But we're almost done.
Will that be on the?
Oh, I was gonna say, I have to leave campus like right now in about 15-20 minutes. So I won't have office hours. If you need to see me, I will be available again later today after 5:30 p.m. on Zoom. So if you need to see me, just send me an email, and well, and then we can just meet on Zoom.
What are the extra credit course evaluations done? Are people
Which one?
filling those out? The weekly one? Really gotta get that extra credit. Thank you.
All right.